What is up, car and tech fans? Welcome back to another garage tinkering video. Some weeks I get to create things that are really cool, and other weeks I get to create things that are useful. Some weeks I get to do something that is both. And that's what I've done this week by creating a desktop CANBus simulator. Because if you're like me and you're designing things like gauges for your car or whatever it might be that are powered by CANBus data, it's all well and good being able to create the designs in LVGL or whatever you're doing, but unless you can actually hook that gauge up to the data that is going to be coming out of your car from your ECU or your body control module or whatever is sending the CANBus data to it, you can't actually test if it functions in the way that you want it to, whether the movement is smooth, whether the incoming data has a negative effect on the FPS of your gauge, all these additional factors. Up until this week, the only way I've been able to test my gauge is to get them and take them out into the car, hook them up to the CANBus in the car and then test them. It wasn't a particularly useful workflow. So I thought, well, why don't I create something that simulates those CANBus signals being sent, or at least the signals that would be sent from a man in the middle, like I'm going to be creating in my 350Z. And if you don't know what a man in the middle is, you can check out this video, which is linked up here, which means then I can simulate everything here from the comfort of my office / growing machining tooling space, which we're going to take a look at in a minute. So let's start by looking at it in action, see what it does. Then I'll talk you through how you go and set it up yourself. You can obviously grab the code from the repo. It's linked down here. And then we'll look at the changes and iterations I want to do to it in the future, because, you know, it is a growing little product. I literally built it in 2 hours this week. So there's still some stuff I want to do. So these are 3 gauges that I've been working on. Spoiler alert, these are going in the triple gauge slot in my 350Z. We have a coolant temperature sweeping needle. We have an oil temperature, does exactly the same, and a speedo. At the moment, after starting them up, they go through their initial load sweep and then they just sit at 0. The reason is they've been programmed already to listen for the CANBus IDs that my car spits out that updates that individual piece of information. But because no CANBus information is coming in, they don't do anything. They just sit at 0. So let's plug in this 4th device. And this 4th device is another one of these ultimate gauge boards. It's obviously got a CANBus transceiver built into it. And it is going to be spitting out CANBus data that simulates exactly what comes out of my car. And we see everything springs into life immediately, and it's sending data at a rate that I've determined from this CANBus simulator to the gauges. What it's allowing us to do is set a minimum and a maximum of a CANBus range. So let's say on this coolant gauge, the range goes from 0 through to 180. They're roughly the kind of values that you would get coming out of the car. And my gauge shows that 0 to 180 as -40 to 140 because of the -40 modifier that Nissan's applied to coolant temperature. And all it does is sweep from the lowest value to the highest value at a rate that you can determine in the code. For the coolant temperature, it's got a speed, as I've called it, of 1. So each iteration, the value goes up by 1, so it's 0, 1, 2, 3, 4, 5, 6, until it reaches the topmost value, and then it returns and it goes back down to its bottommost value. And it just cycles from top to bottom, infinitely, allowing you to see the full range of motion of what happens in your gauge. Now, obviously, for a coolant gauge, this isn't kind of what it's going to look like. It's going to start low and it's going to creep up to a midpoint, about 70 degrees, and then stay around there. That's roughly what it's going to do day to day. But doing it this way allows us to test that the full range works. We don't get any out of bound issues, that the movement looks smooth across the range, that nothing, glitches or intersects with it, anything in a spot that it shouldn't. It just means we can test the entirety of the use of the gauge. The oil temperature gauge next to it, you can see is moving a bit quicker. It's because I've set a speed of 2. So instead of going 0, 1, 2, 3, it goes 0, 2, 4, 6, 8, 10, 12 as it moves up and down. So we get to see it moving faster. Sometimes some values, like let's say you have one of these gauges as an RPM gauge, it is going to require faster moving. So it's important to be able to set that speed value up or down to simulate the kind of speed that that data is going to be coming in. Some things are going to have heavy fluctuations. It might be speed or RPM or throttle position, whereas some things like coolant temperatures would be slower moving, or at least you would hope they will be slower moving. And again, on the third screen, we've got speed. This, again, is being sent to the gauge as a single byte of information, so its range is from 0 to 255, but I've set the range of 0 to 120. It's going up at a speed of 1, coming down at a speed of 1, so it gets to show me the full range in it, how quickly it changes. Now, a single byte range is not the only kind of information you're going to get from a CANBus. As we've looked into it before, there are, I'd say, 3 really distinct types of information. There's your single byte, so your range from 0 to 255. There's a single bit, a thing that turns on and off, that is like the state of something. That might be an indicator, or if your brake light is on, or if your door is open. It has a 0 and a 1 on a single bit that you need to be able to test and read that single bit. Or it has a pair of bytes together where one modifies the other in a big or a little endian. If that doesn't make any sense to you, go and check out this video where I talk about the different kinds of data that come out of CANBus, and you'll understand then what we're talking about. But we need to not just be able to simulate a range. We might want to be able to show, well, what happens when an indicator is flashing on and off and a single bit is flashing from 0 to 1. And I've done that utilizing the position of these XCO pins in the CANBus reader. So if I quickly hook up these 2 buttons to my CANBus reader, I'm going to put one of them onto the XCO pin 5 and the other one onto XCO pin 7. I can then use these buttons to simulate the changing of a state of that 0 and a 1. And I've got it in 2 different forms. A toggle form, which is this button. So if I press this one, we'll see that red spot going on and off. So if I click on, click off, click on, click off. So I can use that to say, well, what happens when this bit changes? So we can just simulate it through the button and just see what it looks like visually when that happens. The other form is a momentary switch. So with this one, if I press and hold the button down, the green one comes on. And if I let go, it goes off. Press and hold, it goes on. Let go, it comes off. Whether you need momentary or toggle, it really determines what it is you're testing. You might want to have something that you can switch on and leave on. In that case, a toggle time type is best. But if you just want to have something where you go, oh, what does it look like if that thing flags? Let's say a check engine light. You might just want to press and hold it, and then when you let go, it goes away again. That allows you to test single bits. And it is also all set up for allowing big and little endians. So if we wanted to change this speedo, let's say I quickly make an alteration to the speedo that allows it to go to a number greater than 255, somewhere up near 1300. That would mean the least significant byte has a range of 0 to 255, and the most significant byte has a range of 0 to 4. Because 4FF in hex, which is what we would be sending, is 1279, so in decimal. So it allows us to test a greater range, and as we can see, it does the exact same thing because the least significant byte runs through the full range from 0 to 255, and then it increases the most significant byte by 1, and it does the same. It runs up until the topmost values, and then it runs all the way back down again. As you can see now, this speedo goes from 0 all the way up to just almost 1300 before coming back down again. I have increased the speed of this, so it's now running at a speed of 5, which means it just, instead of going 0, 1, 2, 3, it's 0, 5, 10, 13, 20. I'll be honest. A big part of the reason that I did this is to allow me to work from the comfort of my office/workshop. And the comforts that I have working in this space is something that is very important to me, and it's also very important to the sponsor of this video, FlexiSpot, who have very graciously helped me out with something for over there, because I don't just work here. I also work on Mega Desk 2, where I don't have a cool, comfortable, ergonomic chair. Until now, because check this out. Wait. This is not the FlexiSpot C7 ergonomic chair, but I think I know where it is. Yep. Now this is the FlexiSpot C7 Morpher ergonomic chair. And this, is so much better. But because it's always getting stolen, it is not currently set up for me. Because this thing is super adjustable. And I love that we can, there we go. Step one, get the neck rest right. Okay, arms. Arms are currently too high. Let's drop them and move them in a bit. The back support isn't quite where I want it, but there are individual adjustments for both the lumbar and the upper back. And then I just want to inflate it a bit more, make it a bit firmer. Now we're talking. This is, oh yeah, now I like this. If, like me, you're going to spend lots and lots of hours at a desk or in a workspace like this, sat down, it is really important for your long-term health and your back and your posture that you have a nice chair that supports you really well. And this FlexiSpot C7 ergonomic chair absolutely does that. Anybody who grabs one of these chairs using the code that is down below can grab yourself an extra $50 off. I think I might just kick back for a minute before I get on with the rest of this video and show you the code, because I've got a feeling this is going to get stolen again pretty quickly. So that was a demo of what this CANBus Simulator does. It allows you to plug this device into your, let's say you're making a micro can and you're going to be displaying your gauges on a micro can, much like I am. It allows us to plug into that micro can and simulate the data that we're going to be sending to our gauges. And really, we're going to use this in one of two ways. We're either going to exactly simulate the information that's coming out of your car. So maybe you're going to replicate a DBC file and say, okay, this is the stuff that my car's sending out, and that's the stuff I want to listen to. Or you're going to set the information that you're going to be specifically setting up for your own needs based on a man in the middle. That's how I'm going to be doing it. At the moment, the IDs that we're going to look at are representative of the stuff that's coming out of my car, but by the time I've finished creating the full application, it won't. My gauges are going to listen to bytes that I've specifically set up in order to reduce load and the amount of data that's being sent to my gauges, because the more CANBus data you send to your gauges, the worse you make your performance. We'll talk about that another time. But so let's take a look at the code and how it works. It's not all that complex, but it is obviously important you have an understanding of how it works. So this is another device that's built off the backbone of my ultimate gauge board. The drivers and everything are all set up off the default code. You don't need to worry about any of that. All it's doing is setting up the board, setting up the CANBus transceiver, the I2C and the XCO for the pin extensions has all been set up just to allow you to use all of the features that are available on the board. The big thing that is important is there's two bits really. There's the structure at the top. So these identify the makeups of the data that we're going to be sending over the CANBus. So we've got our three types are static. So there is another type of static where you basically just send one byte and it never changes. It's just a static byte. A range, which is like we said, it was a number that changes between a min and a max value. And bits, where you can identify the single bits and then hook that bit up to a XCO input. There's whether or not it's got an endian type, if it is a most significant byte, a least significant byte, or if it's not one at all. A couple of button types, non-toggle and momentary. And then my bit config. So each bit, when you're setting up one, it can have a value. So it stores its value, whether it's a 0 or 1. Its mode, which is which one of these modes is it, and if it hooks up to an XCO pin, or if it doesn't, and you just set the XCO pin to -1. Though at this point in time, if you don't hook it up to an XCO pin, it doesn't do anything. Unless you want to set it as 0 or 1 in code and just have it on or off all the time. That's fine, you can do that. So then we just have a structure that pulls all of those types together as a variety of bytes. Then we match our CAN ID with those 8 bytes. And at the moment for this simulator, like I say, there is still stuff I want to do to it, but it is currently only 8 bytes. You could change that if you wanted to do everything as 12 bytes. you can do that. But at the moment, we're running everything off of 8. And then the data rate. So I've been playing with data rates and how fast I send CANBus information to my boards. And I find that if you go beyond 10 hertz, so 100 milliseconds, sending the information 10 times every second, you get quite significant issues between LVGL and the CANBus. It's because they're both fighting for system resources. You end up in the upper 90% of CPU usage. Keeping it around 10 makes things perfectly responsive, but it also means that there is plenty of cycles left which allow LVGL to update itself in an efficient way. So 10 is the sweet spot for me, so 100 milliseconds. You can obviously play with that all you want. Then this bit here is basically where the magic happens. So I have set this up with 2 different CAN IDs, 551 and 555. These are hex codes as they are 0x. You don't have to set them up as CANBus. You could set it up as 123 in decimal, but I personally prefer to work in hexadecimal when it comes to IDs. And then these are my 8 bytes within that ID. I have byte 0, the first one, which is my coolant information, and it's a range type. And then I've set up the variables that create the range. So the minimum value is 0, maximum is 180. The third value is just the stored value. Because we're updating it, we need to hold that value somewhere. So we just store the value. You won't ever really change that. The third value is the speed. So how many integers does it increase or decrease each loop? So in the case where we're doing a data rate of 10, this is going to be increasing by 10 a second. So every second is going to go up by 10 because it's doing 1 every 10th of a second. And the final one is direction. Again, it's just a stored value for the value knowing if it's going up or down the range as it goes up or down. Again, you won't change that. That'll be changed by code. And then finally, the non is the endian type. So these first 3, the coolant, the oil, and the speed, are not endianed. They're just a single byte that sends and controls that information. So they don't need to have a most or least significant byte flag. Now, in the 350Z, this 551 is coolant, and then oil and speed, they're off on other IDs. But as I said, when I am creating this software from my own car, I'm going to be bringing numerous bits of data in like this and sending them in one CANBus ID. It means that I can send, let's say, 8 different bits of CANBus information in one message, as opposed to having to send those same 8 things in 8 messages with a load of additional extra like blank data in there. That's the joys of using a man in the middle. We can manipulate the data in that way. So we just listen to all the incoming stuff from the variety of IDs, amalgamate them together into a single ID, and then just send them on to the gauges. It's a great practice for minimalizing overheads when it's being read by your gauges. So I've pulled the 3 together. And all that means is when it's reading it on the other side, which we'll look at in a minute, when I'm doing the data for coolant, it's listening to ID 551 byte 0. When I do it for oil, it's 551 byte 1, and speed 551 byte 2. Then when we updated the speed to listen to the most and least significant byte, we updated it, as I'll show you in a moment, to use these 2, bytes 3 and bytes 4. So I tell it that byte 4 is the least significant byte and byte 3 is the most significant byte. And then it does all of the maths on the other side to figure out what that value should be. The rest of the information on here we don't actually use. So we fill them in with static, so blank information. It's a static, it's just a value of 0. And then we have another byte setup. This is ID 555. I can't remember why I did it this way, but 555, byte 0 is nothing, byte 1 is nothing, but then byte 2 has got a bunch of bits. So it's got 8 bits. And in here, we've allocated the what the bits do. So bit 0 does nothing. Its default state is 0. It doesn't have a button mode, either toggle or momentary, because it doesn't do anything. and -1 means it's not linked to an XCO pin. So that's bits 0, 1, 2, and 3. Bit 4 starts as 1. Because we're using an XCO, 1 and 0 are flipped, so a high means it's off. So these start off. Bit 4 has a momentary, so press and hold and it stays on, and that's linked to pin 7. And similarly, this one is a toggle type, so press and it toggles between on and off, and that's linked to pin 5. Then again, these other 2 bits are disused, so we'll only care, and I'll show you again in the code that reads it in a minute, about 555, byte 2, bit 4, and bit 5. They're the ones that we listen to for this code. And that's it. And you can like mix and match this stuff together. So if we wanted to be really efficient, we could take those bits there and drop them here. And then we would end up with exactly the same stuff, but all of the information is coming in through one ID. And as you can see, when we start to do that, we can really simplify the CANBus information that's being sent on. It gives us a lot less necessary overheads in programming. But for now, we've got it as 2 different bits here. Then everything beyond that is just the code that makes things work. So the tasks, you can read through these yourself, but all this is doing is running through the entire information, saying what type are you? And based on what type of data it is, it iterates the numbers or the stored values in the way that is relevant based on its speed. So to start with, we've got a range type, and if it's not got an endian, all it does is get the direction, so 1 or -1 times the speed, and then it increases or decreases the value by that amount. So 0, 5, 10, 15 if it's got a speed of 5, or 15, 10, 5, 0 if it's got a speed of 5, but it's coming backwards. Yeah, that's all you need to know. Whereas the most and least significant bytes, it just finds them. So as it runs through all the bytes associated to an ID, it finds if there are most and least significant bytes, and then pairs them together. Then this little bit of code does the same kind of thing. It just loops up through the least significant byte until it hits its max. When it hits its max, it iterates up the most significant byte by 1 and then resets and runs through the way that most and least significant bytes in endian pairs do. Again, you can dig into that a little bit more if you want. It's not particularly difficult. It's just setting directions and setting speeds and then changing one based on the other. After we've iterated it by 1, we build our message. So this is just taking all of that information that we've changed and built upon, associating it to this data block, which is in the style of the CAN stuff that we've done. And then we send that information along at our data rate using TWAI, which is just the generic term for CAN, two-wire automotive interface. And we repeat that every X, so every 100 milliseconds. I don't know why that says 100 hertz. I should say 10 hertz. So that basically does everything. The only other thing at the bottom is this little bit. This just listens out to all of the XCO buttons that are on my gauge board. This is the only bit you might want to change if you're using like not my board and you're using, let's say, a ESP32 Room 1 dev board or something like that. It's got a load of different pins. You would need to change this bit of information because at the moment mine loops through all of the XCO pins and sees if an XCO pin is associated to a bit, and if so, it toggles its state. Other than this little bit, you're probably not really going to want to change anything here apart from setting up your CANBus in the style that you want it. So that's it. As long as you set up your gauges to correctly listen for those same bytes and bits that are incoming from the CANBus simulator, you can really easily test everything on your desktop. That didn't take long at all, did it? I think that's pretty cool, and I found it really useful over the last week. Don't have to go out to my car anymore all the time, which is definitely making prototyping much quicker. If you do want to get hold of this code, obviously it's up on a repo. There is a link down in the description where you can grab it for yourself and test it. There are some changes I want to make in the future. For example, at the moment, when it comes to the most and least significant byte, you can only have that once in any one given ID. So you couldn't have, a range there and then also a range there, because it would get confused by the appearance of 2 most and 2 least significant bytes. It wouldn't know which one to allocate them to. So at the moment, each byte can only handle 1 pair. I will change that in the future. But other than that, I don't think there's really a lot else that needs to be done. It doesn't need to be hugely complex. It just needs to be useful. If you have any questions about this or you want to know anything more about it, please let me know in the comments and I'll obviously do my best to answer you. But I don't think there's really much to go over. It's pretty simple whilst being useful, which is, 2 massive ticks in my book. And if you've got several of my ultimate gauge boards and you're designing on one, you can use your other one to prototype this stuff. It is going to make life so easy for you. Anyway, I hope something good happens to you today. And I'll see you next week, Wednesday at 2 p.m. Take it easy, peeps. Bye-bye.